you guys to try some programming right on the spot. Even if you don't finish writing a program that we start talking about, I will finish it, and we can all kind of talk about it together, and I'll kind of show you some pitfalls and things like that. There will be lots of opportunities to practice in this class at various degrees of granularity. And then there's also lots of opportunities that I have in the handouts to do extra practice at home, and I'll kind of show you some different resources as well. The reason why I stress participation and practice is because part of the reason you're here is you want to learn how to program, right? You don't know how to program yet. And programming is actually a skill, right? It's like math or reading. It's something that you have to practice. You can't just watch me type in a bunch of lines of code, and then when it comes time to do the quiz, you'll automatically know how to do it. You need to do it often, more and more, so that it becomes sort of second nature, right? So the three big things you'll get out of this class are knowledge of concepts. Obviously, we're going to learn some computer science ideas, programming skill, and problem solving skills. Lectures and exams basically help you test your knowledge of concepts and help you get knowledge of concepts. Finger exercises give you the programming skills, and the problem sets help you with problem solving. Basically, if you're given an English version, of a problem in English, how do you go from that to thinking about what computer science concepts can I apply? And then after that, how do I take those computer science concepts and actually do the programming? So what are some topics we'll be covering? We will be, at the core of it, learning computational thinking. So in the future, when you encounter a problem, you can, your first thought shouldn't be, how do I kind of mathematically solve this, or how do I brute force, right, manually solve this problem? How can I apply computation to help me solve this problem? And throughout these lectures, you're going to see some examples of us applying computation to a problem you might have already seen and maybe solved mathematically, which is pretty cool. Obviously, to get to that, we're going to learn the Python programming language. Once we get the basics, we're going to see how we can start to structure our code to look a little bit better, so we don't just have a bunch of code dumped in a file. We're going to start to organize our code and see how we can make it neat, readable, and modular. And then towards the not in this lecture, but in a couple lectures and as a theme throughout this class, we're going to look at some algorithms. They're not super complicated, but they're kind of the base algorithms for a bunch of algorithms you might see in the future if you decide to take more CS classes. Lastly, towards the end of the class, we're going to see algorithmic complexity, which basically means we're going to start asking or trying to answer the question, how do we know the programs we write are efficient? Right? We can write programs, but how do we know that they're fast? And how do we know that they don't take up all the memory in the computer? So things like that. Comparing different algorithms that do the same thing against each other. So if there's no questions, again, as I said, a bunch of this information is already in the handout, plus more. We can begin. OK. So let's start by talking about knowledge. Declarative knowledge is a statement of fact, and a lot of us probably in math and in the past have worked with declarative knowledge. But this is not how computer science, this is not how this class works. In computer science, what we do is we work with imperative knowledge, which is basically a recipe, how to do something. And when we're programming, all we're doing is writing a recipe for the computer to do something. That's it. So here's a numerical example. The first statement is a declarative statement, right? The square root of a number x is y such that y times y is equal to x. There are many possible values for x and y that this statement can be true, right? But if we gave that statement to a computer, it wouldn't know what to do with it. What we need to do is tell the computer how to find the square root of a number, and then tell us what the square root of that number is. And so the computer then needs a recipe. So the recipe, a really simple one for finding the square root of a number, is steps 1, 2, 3. So what we do is, let's say we want to find the square root of 16. We obviously know it's 4, but the computer doesn't. And so we give it an initial guess. Let's say the guess is 3. How do we go from there? So the steps we follow, step 1, If 3 times 3, 9, is close enough to 16, we can stop. It's not really close enough for me, so let's keep going. Step 2. Otherwise, so we're going to make a new guess by averaging g, which is our original guess 3, and x over g, which is 16 over 3, right? 16 was the square root we wanted to find. So our next guess is 4.17. Okay, using the new guess, repeat the process until we are close enough. So we go back to step 1, that's the first part of the process. We find guess squared. 4.17 squared is 17.36. So now we say, is that close enough? Not really, it's 17, it's not really even close, 16. So let's do it again. We make a new guess by averaging 4.17 and 16 divided by 4.17, right? That gives us our new guess, 4.0035. Okay, next step, right? Using the new guess, we repeat the process. So 4.0035 squared is 16.277. Is that close enough to x? Yeah, I could be happy with this. I could stop there because we're within sort of plus minus 1, so I'm okay with that. But if we wanted to be within plus or minus 1 times 10 to the negative like 6 or 7 or something like that, then we would continue the process. So really what we had there is an algorithm, right? It's a sequence of steps, step 1, step 2, step 3. There's some sort of flow of control, right? We had a place where we said if this is, if the guess is close enough, then, we can stop. Otherwise, we do something else. We had another flow of control where we said repeat this thing, right? So we're kind of not going linearly, but we're changing the flow. And then lastly is a way to stop, right? We don't want the algorithm to go on forever. We would like to stop at some point. And the stopping point, I was kind of vague about it, but it could be, when we were within plus or minus 1 of the actual answer. And so, right, recipes are basically algorithms, right? My grandmother was basically teaching algorithms when she would teach me to bake a cake, right? She didn't call it that, but she was, really. And so even recipes have that same structure. There's a sequence of steps. There's a flow of control, like if you don't have egg, use egg substitute, or repeat this, repeat sticking a toothpick to see if it comes out clean every minute, or something like that. And then there's a way to stop, right? When the toothpick comes out clean, you take it out of the oven and you eat it. And so computers are machines that execute these algorithms. They're actually dumb, right? Computers are not very smart. They don't make decisions on their own. They just follow these sequences of steps that we told them to do. Computers are good at storing lots and lots of data, right? We can't really do that, but computers can store gigabytes of storage, terabytes even, and computers can do operations really, really quickly, which is something we can't do, right? They're good at those two things, but they're not very smart. They can't make decisions unless they're told to make the decisions. So really, the computer only does what you tell it to do. And that's one of the big ideas that I want you to come away from this lecture with. The computer only does what you tell it to do, right? The sequences of steps that you tell it to do, that's the only thing it follows. So a little brief history, just to kind of make you appreciate Python programming language before we actually get started with it is, so before the 1940s, we had these things called fixed program computers, okay? Like a pocket calculator is an example of that. Every button was an operation. You could, in the little screen, you could use parentheses to put a bunch of different operations together, but there was no way to sort of store all these operations together to later put in different inputs for that same sequence of operations. You had to input it every single time, input those sequences of operations every single time. After the 1940s, stored programs computers came into play, and they were able to store instructions to do things as data, okay? And there was a special program called an interpreter that executed these instructions. It knew how to follow simple sequences of steps. When the program told it to go to a different location, it did. So it was basically executing these instructions. And the instructions that it did were arithmetic and logical, so addition, subtraction, things like that. Simple tests like checking for equality between two values, and moving data, so taking this value and putting it at a different memory location. So I just wanted to give you a really brief overview, and this is not super accurate, but it gives you a sense of how exactly things happen low level in the computer. So the computer basically has memory where things are stored. It has an arithmetic logic unit that does operations. It knows how to add things, subtract things, multiply things, compare things. And then it has the control unit where this program counter is set. And this is where you put a program in. So let's see if this works. This is a program. And up here is our memory. So we have a bunch of memory locations, 3, 4, 5, 6, 3, 4, 5, 7. And at each of these memory locations, we have some values stored, pre-filled. So when we first run this program, what ends up happening is the interpreter sees the first instruction, add the values at 3, 4, 5, 6 and 3, 4, 5, 7 together. So it goes to these memory locations here, grabs the 3 and the 4, and sends them to the arithmetic logic unit. The ALU knows how to do the addition, so it adds 3 plus 4, 7, and sends the result back here. Now, we never told it to store that result anywhere, but the next instruction says store the value you just got back from the ALU at this memory location, 3, 4, 5, 8. So the next step basically takes that 7 and stores it at memory location 3, 4, 5, 8. Super tedious. All we did was add 3 plus 4. We do that again. We add the values at 7889 and 7890. So it goes in the memory, it grabs the 5 and the 2, sends it to the ALU. The ALU calculates it as 7, brings it back, and then we store that in location 7891. Okay? And then after that, all we've done is 2 additions. And then the next instruction says compare the values at memory locations 3, 4, 5, 8 and 7, 8, 9, 1. So we're going to compare the 7 with the 7. The ALU, again, does this comparison and says, all right, well, 7 and 7 are equivalent, so this is true or whatever it wants to give back to the interpreter. And then the last instruction here we have is print the result of that comparison. So we print true because they were equal. Right. Again, super high level, but it kind of gives you an appreciation for programming languages these days, right? This is very tedious to write if we had to write programs in this manner. Alan Turing a long time ago showed that you can compute anything with actually an even more basic set of primitives, not addition, subtraction, but instead with a tape, you would actually have 6 primitives. Move the tape left, move the tape right, read the value at the tape, put a value on the tape, erase the value from the tape, and no operation. And so since he showed this, what the result of it actually was is down here. Anything computable in one language is computable in any other programming language. So if we had some program written in Java, that basically boils down to, right, something super long, but something that is made up of these 6 primitives. That means that if we boil down this program to these 6 primitives, we can build back up the same program in a completely different language. And that's really powerful. That's a really cool statement. Now, we're not going to be working with those primitives. We're going to be using the Python primitives, which are more convenient, and they allow us to do a lot more things in much less time. I'm going to do a little comparison as we talk about the primitives of Python with English. So in English, some of the primitives might be words, or even we can do letters or characters, but we can say it's words. With characters, we can build up words. With words, we can build up sentences. With sentences, we can build up stories. With stories, we can build up books and things like that. In programming languages, the primitives are numbers, sequences of characters, operators like addition, multiplication, division, checking for equality, checking that something is greater than, things like that. So once we have these primitives in a language, we can start to build up the syntax of the language. So in English, having something like noun, noun, noun doesn't make any sense. right? Cat, dog, boy doesn't make much sense. It's not syntactically valid. But noun, verb, noun is syntactically valid, right? Similarly, in programming languages, we can have two objects kind of side by side. So here, this is a sequence of characters, H and I, and this is the number 5 right beside that sequence of characters. But that doesn't make any sense, right? What does it mean to have this sequence of characters and that number right beside it? It has no meaning in Python. Instead, what we have to do is we have to add an operator in between these two objects. So here, we add a little star operator in between the sequence of characters hi and the number 5. And in Python, the meaning to this is I want to repeat the sequence of characters hi, hi, 5 times. So this would basically give me hi, 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 hi. So once we have sentences in English, right, and expressions that are syntactically valid, we can now talk about the static semantics of the language. So in English, saying something like "I are hungry" is syntactically correct, but it's not static. It's not. Sorry, it's not. It doesn't have good static semantics, right? There's no meaning. There's no meaning to that because the "are" is for you or plural. Similarly, in programming languages, and this will differ depending on what programming language you use. Here, in the previous slide, we saw that you can use the star operator between the sequence of characters and the number, and that meant repeat that sequence many times. But if we use a plus operator in between the sequence of characters and a number, that doesn't have any meaning in Python. So it has a static semantic error, even though it's syntactically valid, right? We have operator, object, operator, object. So far we've been able to find really nice parallels with English, right? The English language and the programming languages, but this is kind of where things break down when we talk about the semantics of a language. So in English, you can have many different meanings, right? The chicken is ready to eat means let's eat this chicken, or the chicken is ready to eat means the chicken wants to eat something, right? Programming languages, there is no multiple meanings to a program that you write. Because the computer, the machine, the language follows the set of instructions to a T, there is no ambiguity about what it needs to do, right? It just follows the instructions and does what it needs to do to the end, till it reaches, it terminates the program. And so programs only have one meaning, but the problem is it might not be the meaning that you intended it to have. And that's when things start to go wrong. We can have syntactic errors in our program, spelling errors, indentation errors, things like that, and those are easy to catch. Static semantic errors are 90% probably easy to catch. But the problem comes in with the semantics, right? The meaning that you intended this program to have might not be what it's actually doing. And that's where most of my errors happen, and that's where I get super frustrated when I program, and that's probably where you guys will get super frustrated too. Because you write a program that you think is doing one thing, but instead either it crashes right away, or it runs forever and doesn't really stop, or it terminates, but it gives you an incorrect answer. It's not what you were expecting. And we'll talk about this in a while, in a few lectures. So when we write programs, we're basically writing sequences of definitions and commands. And we're going to write these either in a file editor or in a shell. The first, today at least, we're writing in the shell directly. And half of tomorrow we'll write in the shell, because we're not really writing any. We're not really writing many lines of code. I'm just going to be showing you some really quick things that we can do with the Python programming language. So hopefully you all have installed the programming environment. This is the code editor. So tomorrow we'll start working in here. But for today, we're really just going to work in the shell. And even in the future, you can still type commands in the shell. I find the shell very useful if there's just something really quick that I want to check, that I don't want to write a program for and then run. It's just like a simple command that I want to check to make sure it's doing what I think it's doing before I insert it in my code editor. So here we have this. Right, so mine is, I guess I'm using the white theme just because I find it easier for you guys to see. This is the file editor, and this is just a bunch of expressions, a bunch of code that we're going to type in today. And we're going to type it in the shell today, so the thing on the right-hand side. Okay, so what exactly do we do when we write a program? At the base of it, we're going to create objects inside our programs, and we're going to manipulate them. That's it. That's what programming is mostly about at its core. Now, when we create objects, it's important, this is kind of something we're going to come back to again and again in a kind of more high-level setting, but right now, what I want you to understand is that when we create an object has a type, okay? And the type that an object has tells Python the things you're allowed to do with that object. So here are two examples. The number 30, it's a number. The type, we're going to talk about it in a bit. The type is an integer. It's a whole number. But basically, what are the things we can do with this integer, with this number? We can add it to another number. We can subtract it to another number. We can take it to another power. We can take some other number to this power of 30. Right? A bunch of sort of mathematical operations, as you would expect. So that's pretty straightforward. What about this one here? This quotation, capital A, lowercase n, lowercase a quotation. So this is something we'll talk about next lecture. It's called a string, and it's a sequence of characters. The quotations tell Python it's a sequence of characters, and the characters, part of it, are capital A, lowercase n, lowercase a. The kinds of things I can do with this string are not the same kinds of things I'm allowed to do with a number, right? If I tried to take Anna and divide it by the sequence of characters Bob, Python would complain very much, right? Because you can't divide a string by another string. A sequence of characters doesn't make sense to divide it by another sequence of characters. Similarly, I can't take Anna to some power, right? I can't multiply, or I can't multiply by itself, things like that. But the kinds of things that I am allowed to do on a sequence of characters is different than the kinds of things I'm allowed to do on a number. So the things I can do with a sequence of characters is I can say, well, what's the character at the first position? What's the middle character? How long is the sequence of characters, right? How many characters do I have? And so now you can see that the type of the object is actually really important. Python uses it to know the kinds of operations you're allowed to do with it. And so there's actually scalar objects, and these are Python's primitives, numbers and truth values. And there are non-scalar objects. We're not talking about these yet. We'll talk about these in a few lectures, but these have some sort of structure. So for example, a list of numbers has a structure because there's a number at the beginning of the list, there's a number at the end of the list, things like that. But a number itself doesn't have a structure. It's just the number. So what are the types of the scalar objects? What are the types of the primitives in Python? Integers. So number 5, 0, negative 100, 1,000,000. Float is another type. It represents all the real numbers. So 3.27. 2.0 is a float because it has a decimal number, even though to us that just means 2. But to Python, if you put in 2.0, it says that's a type float. Negative 3.14159, things like that. Bool is a Boolean. It represents truth values. And there's only two possible values that a Boolean type has. True and false. And it has to be capital T true and capital F false. And the last one is this none type type. It's literally called none type. And it has only one special value, none. We're not going to talk about it for a bit, but we will sometime in the future. So to figure out the type of an object, when you create that object, you use the type command. So we can say something like type, parentheses, and this is a command. And inside the parentheses, you say, what do you want to find the type of? So if we do type of 7, it tells me it's an int. And if you want to do the same command again, I hit the up arrow, and it automatically puts in what I wrote previously. And then if I want to do type of 0.0, it's a float, because there's a decimal point. So this is basically what I said. So we type this in the shell, and the shell tells us what the output is. So just to reiterate, int, float, bool, and none type are types of objects. And there can be many different objects you can create of that type, right? So if you think about it, ints and floats, we basically have an infinite number of objects we can create of those types, right? Because we can have 0, 1, 2, 3, 100, 200, 300, a million, right? And all the negatives. There's almost a infinite number of values or objects that we can create of type int and float. But bool, there's only two. The truth values true or false. And the none type, there's only one, this none, right? So that's the type. And these are the possible values, possible objects we can create. You try it. So you can just yell out the answers. There's nothing to type unless you want to check yourself. So what is the type of 1,234? Int, type of 8.99. Float, type of 9.0. Float, type of true. Bool, and type of false. Bool. Perfect. If you ever wonder what the type of something is, you type it in here. Just, you guys are doing well. Type is bool. Type of lowercase t true is an error. Just wanted to point that out, just to reiterate the fact that capitalization matters in Python. This is our first error, by the way, guys. Very exciting. The error is a name error, and this is the message associated with it. You also know that it's something special in Python when you have color-coded stuff. So you see capital T true, capital F false are this dark blue here, right? Whereas anything that's not special in Python is just black, right? So type is a special command, right? This is a float, so you see they're color-coded. Okay. So once we create objects, one thing we can do with these objects is to cast them to a different type. Now this is a little bit maybe confusing because we're not actually changing the object once we've created it. So once we create the integer 3, it's there in memory. If we cast that integer to a float version of it, we're creating a new object in memory. We're not changing the 3. The 3 already exists. We're just getting the float version of it and storing it as a new object in memory. So when we do float 3, this is a command that gets for me the float version of the integer 3. Okay? So that will give me 3.0. So for example, right, this is what I had, float 3. Right, the output is 3.0. If I do int of 5.2, it truncates it, and it gives me the integer portion of this float. If I do int of 5.9, it still truncates it and gives me the integer version of this float. It doesn't round, right? I'm just asking for the integer version of this float. Some operations, like round, is an operation